This is quite an interesting theorem in group theory, so let's give a proof. The statement says that if G is a group such that every non-identity element has order 2, so G squared is the identity for every G, then G is abelian. I'm about to give a proof of this theorem, so if you want to try it on your own, because it's a pretty nice thing to try to figure out on your own, then stop here, come back to it. Otherwise, the proof is here in 3, 2, 1, proof! Let G and H be arbitrary elements of the group G. We want to prove that G times H is the same as H times G, so G is abelian, it's commutative. So first, note that GH times GH is the identity because the order of GH is 1 or 2. Maybe GH is the identity, in which case identity times identity is identity, or it has order 2. GH squared is identity, so we have that equality. Also, GH times HG, by associativity, I can write as G, H times H, G, but H times H is H squared, so that it has to be the identity, and times the identity, I get G times G, and G times G has to be the identity because, again, every element has order 1 or 2. Therefore, we've shown that GH times GH is the identity, and GH times HG is the identity. This equation tells me that GH is an inverse for GH, but also that HG is an inverse for GH. But there is a uniqueness of inverses in a group. Therefore, the inverse is GH and also HG. So what I get is that GH is equal to HG. And since G and H were arbitrary, G is abelian.